Welcome to this another new lecture for the section 2 error propagation, lecture 3 nonlinear function. In the previous lecture 2 of section 2 we have seen that how actually the error propagates in case of a linear function when the measured quantity is related with the computed quantity in a linear manner. In this section we will see the case of nonlinear functions. Now let's say that y is a computed quantity and x is the measured quantity, and the relation between y and x is a non-linear one. And again say xt represent the true value of x and yt true value of y, and dy error in y and dx error in x. We can write yt equal to xt square also as per the relation. Now we can write y as here yt plus dy, and x we can write x plus dx, sorry xt plus dx ka whole square. Now just solve it. Yt plus dy equal to the xt is the true value of x plus dx ka whole square 2xt dx. So that xt square can be written as the yt, so those both yt gets cancelled out, so the remaining is the dy, so 2xt dx plus dx square. So that is the final error in the function dy. So that is the final error in the y. Dy is represented by 2xt dx plus dx ka whole square. So here if you observe that 2xt dx is the partial, like we wrote y equal to x square. So if you take the derivative of it's 2x, so that 2xt dx is the derivative of y with respect to x at, you can say, at xt. So then you can write dy dx if you derivative at xt. So dy equal to, you can write dy by dx plus dx ka whole square. So if you recall the linear case, in linear case dy was equal to like a dx, and a dx was also the derivative of that y equal to x plus b, and dy equal to that, if I write completely here. So for the linear case this was the kind of a error term. Now error, actually this was the error propagated into the calculated function y. But if you see here in that non-linear case, this is similar to the linear one, but one additional term of dx whole square is also added here. Generally the amount of error, that is the dx, is very less, and when you square it, it also becomes very minimal. So in most of the cases we neglect this error and remove, actually do not adopt this last term and just calculate the error only by this first term, and assume that this dx square is negligible. So here I will try to explain you this scenario of 2xt dx plus dx square if we neglect this dx square term. So graphically, if you can see that the red one is the non-linear function. This is a non-linear function. Okay, this is the non-linear function. Linear. Now just look, if the yt is the true value represented here, xt is the true value. So that yt is a true value minus that y is the measured value is actually the dy. dy is the error in the measurement, yt minus y, and dx is the measurement error in the xt minus x. So what we are doing here by neglecting a second term dx square, so rather than evaluating this nonlinear function at p point, we are evaluating this at a point p dash, which is located at the tangent at a point here t, the true value that crosses this point, a tangent to that point, that p dash is located at this tangent. So that difference between y minus y dash is the dx square. So generally this dx square is a very negligible term, so we neglect it. Now see through the example. Let's assume that the problem is that we want to calculate the area of this square, and we are using a 30-meter tape. After measurement, the length of the side comes out to be 50.170 meter. If after the measurement it has found that the tape is short by 0.030 meter. So now if we calculate the area, let's say area is y and that measurement is the x, then y equal to x square. The area y is equal to the 50.170 square. Y is equal to 2517.0289 meter square. So here we have not rectified for the error. We have just simply calculated the area by the measurement. But after that, if we know, now we know that after measurement the tape was short by 0.030 meter. So now correct for the error, or we can say we are now eliminating the error from the measurement, that is x. So we know that the tape was short by 0.030 meter. So actually that now if you say 30 meter minus 0.030, so the tape was actually 29.970 meter long. So now what would be the actual distance measured by? You can simply say 29.970 divided by 30.00 into the measured distance 50.170. So that is a 50.120 meter. So 50.120 meter is the actual distance after applying the correction. So now we have the corrected distance. So what would be the yt is the true value of yt xt square. We know that the xt now has the 50.120, that is 2512.0144. So this is just kind of a very simple problem. So we can actually eliminate this error initially in the measurement, and now we are calculating the true value of the area, that is the yt. So we can also now know the error. What is the actual the error in the first place? Y minus yt 25. So now look that the dy here is equal to the y minus yt, and the value of dy is that. So it was a very simple problem, so that we have, indirectly we also solve this. And the dx, that is the error in the x, is x minus 60. This comes. Now we will actually apply the formula or the function that we actually derived. That was the dy 2xt dx plus dx square. So we know there's 2. Xt is this value of the x. Corrected value is the true value of x, that is a 50.120 that we also used here, and dx is the error that we can calculate by this. Okay, we know the measured value and we also know the corrected value, so we have known the dx plus dx square. So when you solve it, these two values, the directly computed values, and through this function, actually the error in the y propagated is same. So in the second, we also can see that if we drop a term, what would happen to that? 2xt dx. If I calculate for this, then that is 50.120 to this value is 0.050, 5.0120. So if you compare with this 5.0145, this value, if we neglect the term dx square, the difference between these two value, if I write, so if we neglect the term dx square, we are getting this value, and with the complete full including dx square, we are getting this value. So the difference between this, when we see the actual final impact or the difference, that is 0.025 meter square. That is very, very negligible. So after just that example, one more thing is left for the non-linear function. Let's suppose the y is a function of more than two variables, x1 and x2. Earlier we took the example of rectangle where y is equal to x square, is y in that function is the function of only one variable. Now that take an example of, sorry, I said that rectangle, we took the example of square. Now take the example of rectangle where one side, you say L and B, both sides are length and width are different, then the y would be the function of x1 and x2. Then what would be the dy? That is the error propagated in the function. So that is given by this dy is equal to the dou y by dou x1 dx1 plus dou y by dx2 to dx2 plus dou y xn. So it is a generalized function. If you have the n number of variable up to that x1, x2, xn, that in this way you will get the error propagated in the dy. In the similar way we derived dy, you can also derive this function. So the key takeaway from this lecture is that for the nonlinear function, the error propagated is represented by this, and in case the function y, that is the computed function, is composed of more than one variable like x1, x2, xn, then the dy will be given by this equation where the partial derivative of function with respect to x1 and this is the partial derivative of function y with respect to x2 and that error in the dx2 value. This way you can get the final propagated error in the function dy. And also we generally that dx square is a very small quantity, or you can say it is a negligible quantity, so we can neglect this. And in this lecture we also seen by example that how actually the error in the measurement will get propagated into the final computed quantity by giving the example of area calculation.